Okay, let's talk about action potentials now. So if you remember, we said that the action potential is the electrical signal that neurons use to communicate over long distances very quickly. So in the last chapter, we talked about the membrane potential. And so the membrane potential, remember, is just the difference in electrical potential on the inside of the cell versus the outside. And so an action potential is just, as we will see, is a special type of membrane potential. So to observe an action potential, all you need to do is record the membrane potential of a neuron. So here we have a neuron and we have a recording electrode in that neuron. So we're recording the membrane potential over here. So right now, the membrane potential is at rest, or the membrane potential is basically a flat line. And so we say that this neuron is at rest. So by definition, whatever the membrane potential is the resting potential. So over here, this graph represents whatever the current membrane potential is. So let's say this line right here, maybe it's minus 65 millivolts. Doesn't actually matter what it is, but by definition, if the membrane potential is more or less flat, then we call this the resting membrane potential, or just the resting potential. Now, in reality, of course, it wouldn't be totally flat like this. For a typical neuron, you might see little fluctuations up and down, but as long as there aren't any big, drastic changes in membrane potential, we say that this neuron is at rest. But then, if you are waiting long enough, you will eventually probably see a change in the membrane potential that's very, very sudden, where the membrane potential very quickly goes up well above zero. So let's say that this is 0 millivolts. So the membrane actually becomes positive. So it could get, as positive as, let's up here, it could be plus 40 millivolts. And then suddenly goes way back down. So all in the space of really just a couple milliseconds, you have the membrane potential shooting straight up and then going straight back down again, and even going back down as quickly as it went up, and even going back down below rest for again another millisecond or so. And that behavior, that sudden change in the membrane potential, is what we call an action potential. Now, of course, in an actual real life neuron, you would not see it as neatly laid out like this. You would probably just see it as a straight line, just a spike, because it's so quick it goes straight up and straight back down again. And you can actually induce action potentials in a neuron. You can force a neuron to create action potentials by injecting current. So what that means is you have, in addition to your recording electrode, so our recording electrode is just telling us the difference in membrane potential between the inside versus the outside. But then you also have a stimulating electrode, which again can just be another pipette. In some setups, the recording electrode and the stimulating electrode are the same. But in this case, I've got a separate stimulating electrode, and that is applied to, a current is applied to that electrode. And by definition, we're injecting positive current into the cell, which just means we're making the inside of the cell more positive than it normally would be, which means you are depolarizing the membrane. So anytime you make the membrane potential less negative or get closer to zero, we say that it is depolarizing. So you're artificially forcing the membrane to become depolarized by injecting current. And when you do that, up to a certain point, once you inject a certain amount of current or depolarize the membrane to a certain point, the neuron will start producing action potentials, and it will keep producing action potentials as long as you inject that current. So that's what we're doing here. Here you can see this is our injected current. So the amount of current is here, and you can see the time when we started, we turned on the stimulating electrode right here, and pretty much at that same moment, the neuron started producing this train of action potentials. So each vertical line here is a separate action potential that gets produced one after the other. So if we could zoom in on a single action potential event, it would look like this. So we are just graphing, like I said, the membrane potential in millivolts over time. And so as long as it's flat like this, again, we say it's at rest. And then as soon as the action potential begins and the membrane potential starts to become less negative and more positive, we say that the action potential is in the rising phase. So this is the rising phase, when the membrane potential is going up away from the resting potential. And during the action potential, eventually, again, this is all very quickly happening. So we're talking about less than a millisecond so far. The membrane potential goes above 0. So now the inside of the cell is actually positive compared to the outside, but not for very long. But while it is, we say that the action potential, this is the overshoot phase of the action potential. And then almost instantaneously, again, it doesn't spend very much time up here above 0. It starts going back down again. So the membrane potential starts becoming more and more negative. And we call this the falling phase. And the falling phase continues all the way past the resting potential. So again, the resting potential for a typical neuron is maybe about minus 65 or so. Doesn't actually matter. Again, every neuron may have its own different resting potential. But at the end of the falling phase, the membrane potential actually goes below that resting potential. And so for about a millisecond or so, we're in the phase of the action potential called the undershoot. And then gradually, relatively gradually, compared to the speed of the rising phase and the falling phase, the membrane potential returns to rest. So that those are the phases of the action potential, the parts of the action potential: the rising phase, overshoot, falling phase, and undershoot. And so we will go through and explain what's happening at the membrane for each of those phases. Now, some important points about generating action potentials. So like I said, you can create action potentials by injecting current into a cell or by depolarizing the membrane of the cell, but you have to depolarize it beyond a certain point. So in other words, here we're injecting different amounts of current. So in the first phase here, we're injecting a relatively small amount of current. Doesn't matter how much, but the point is that this is then the change in membrane potential. So here we're recording membrane potential, and so the change in membrane potential due to that small amount of current will depolarize the membrane. So the membrane goes from minus 65 to who knows, maybe minus 60 or so, minus 50. But whatever it is, it's not enough to generate an action potential. So the membrane potential goes up, but it's still flat. So there's no action potential yet. And so what that means is that action potentials only occur if the membrane is depolarized beyond what's called the threshold. So there's a certain minimum amount of depolarization that you have to get to before an action potential can occur. And we'll talk about why that is later. Now, once you do raise the membrane potential or depolarize the membrane above the threshold, you will get an action potential. And in fact, as long as you keep injecting current, so here we're injecting current for this entire stretch of time here, the neuron will continue producing action potentials as long as the membrane stays depolarized. In fact, again, this is usually in an artificial situation, so the neuron will keep firing action potentials as long as it's alive, which means as long as it has energy and oxygen, it will continue to produce these spikes. By the way, that's another term for action potential because that's what they look like on the graph. They look like these big thin spikes. Sometimes you'll hear action potentials referred to as a spike. Also, when we say that an action potential is produced, sometimes you'll hear the word firing. So when we say an action potential or a neuron is firing, that means it's producing action potentials. Again, firing, spiking, these are all just different terms for a neuron producing action potentials. And then the other thing you can learn by generating action potentials is if you continue to increase the current. So now we've gone from, again, sort of a small amount of current to a medium amount of current to a relatively large amount. We've depolarized the membrane even more. the neuron will keep producing action potentials, and the action potentials look the same. So the height of the spike, the duration of each action potential is basically the same. The only thing that really changes is the firing rate, which is just the number of action potentials per second. So here, this whatever block of time this is produced 5 action potentials at this level of depolarization, and then over here in the third situation. So again, this depolarization led to 5 action potentials in this time block, whereas this larger degree of depolarization, now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So more than double the firing rate, assuming these are the same amounts of time in each case. So that's what increasing the membrane depolarization will do. Now we'll learn later that there is a theoretical maximum to the firing rate. So there is a point beyond which you can't start a new action potential until the last one is basically finished, and we'll explain why that is later. So to begin to understand what is happening in the neuron during an action potential, let's imagine an ideal neuron. By ideal, I mean that so to understand what is happening in the neuron during an action potential, let's imagine an ideal neuron, and by the ideal I mean it's very simple. So it's first of all, it's just a perfectly spherical cell, and for now we will imagine that it only has 2 types of ion channels. So it has sodium channels and potassium channels. So the sodium channels here we're coloring in blue, and the potassium channels are the pink ones. And right now in our ideal cell, all of the channels are closed. Whoops. So we keep all the channels closed, and that means that there is no current of any kind, no current going in or out of the cell. And the way we describe current in terms of ions is the current for any ion. So here we're saying the potassium current. So remember, I is the symbol for current. So when we say I sub k, that just means the potassium current is equal to the conductance for potassium. So G is conductance, remember, and that's a function of the number of open channels. But to begin with, this number is 0 because all of these channels are closed. And then the current is going to be proportional to that number times the difference between the membrane potential and the equilibrium potential. So remember that the membrane potential is just whatever the difference is between the inside and the outside of the cell, and in terms of electrical charge, and the equilibrium potential is always going to be a function of the concentration gradient for that ion. So if we're talking about the equilibrium potential for potassium, it's going to be a property of the concentration difference for potassium. A typical cell would have a large internal concentration of potassium compared to the outside, and so it will have usually a large negative equilibrium potential for potassium. So here in our ideal neuron, we're saying that the equilibrium potential for potassium is -80. And now we don't know, for mathematically, we can't really say what the potassium current is. I mean, we can say that it's 0 because the conductance is 0. But what we're then going to do is start opening some potassium channels. So in our ideal cell, again, we're opening potassium channels. Now, initially, the actual membrane potential would be recorded as 0. In reality, the membrane potential would not be 0, even in a cell with no no open channels. So you can't actually have a cell with where the ion permeability is actually 0. So there's always going to be a small membrane potential. But in this ideal cell, there is none. And so as soon as we open those potassium channels, again, we recall what happens when you open a channel. The ions will flow through, and they will flow according to their concentration gradient and to the electrical potential. So in this case, potassium is more concentrated inside the cell, so it's going to flow down its concentration gradient out of the cell, and it's also going to move according to its equilibrium potential. So because the equilibrium potential for potassium is -80, And as long as the membrane potential is not equal to minus 80, the ions will move. So again, now we can go back to this equation. We can figure out the potassium current and say that the potassium current, again, is equal to the conductance times the difference between the membrane potential and the equilibrium potential. So now the conductance is some number greater than 0 because we've opened some channels. So that means potassium ions are allowed to flow through. And this difference between the membrane potential and the equilibrium potential is going to be some positive number because, again, the membrane potential is initially going to become reach some positive number, and actually it's going to be negative. And because remember, as potassium ions leave, the inside of the cell will become more negative, whereas the outside will become more positive with more potassium ions out there. And so the membrane potential will become negative. But the membrane potential, the current is proportional to the difference between the membrane potential and the equilibrium potential. So as long as the membrane potential is less than or is not as great as minus 80 millivolts, then this difference will be greater than 0. So the potassium current initially will be greater than 0. And by the way, we define current in this case as positive charges leaving the cell. So if we say the potassium current is greater than 0, that means that there are potassium ions leaving the cell. Okay, so initially we have our membrane potential becoming more negative, and we have a potassium current that's positive. Now, the question that you should ask yourself before we go on is what will happen if we keep going? So if we just leave these channels open, what will happen to the membrane potential, and what will happen to the potassium current? What will happen to all these numbers? So again, we leave the channels open, so that means the conductance for potassium stays at some positive number. And eventually, as the membrane potential becomes more and more negative, the question is, will the potassium ions keep moving out of the cell forever, or will they eventually stop? Will they eventually go back in? And if you remember from last time, by definition, when the inside of the cell becomes so negative that the potassium ions start to be drawn back in, then that will be the point at which the potassium ions will be at equilibrium. So when the membrane potential becomes equal to the equilibrium potential for potassium, then again, we can do it mathematically down here. The difference between the membrane potential and the equilibrium potential will be 0. Therefore, it doesn't matter what the conductance for potassium is. Now the current for potassium will be 0. So when the membrane potential becomes equal to the equilibrium potential for potassium, potassium current stops. That's what equilibrium means. Now, that doesn't mean that the potassium ions can't go in or out of the cell. As long as the conductance is greater than 0, the ions are free to go in or out. But they are at equilibrium, which means that the net inward movement of potassium is going to be equal to the outward movement of potassium. So to show this in clear detail, let's go to our little Nernst equation simulator, our Goldman equation in this case. So again, in our ideal neuron, we said that the equilibrium potential for potassium was minus 80. So actually, let's go ahead, let's switch to the Goldman situation, and let's set this as a generic cell, which gives us a, in this case, it's a equilibrium potential for potassium of minus 87. Again, it doesn't actually matter what the number is, as long as it's a large negative value. And so up here, you can see the membrane potential, the black line, and you can see the equilibrium potential for each individual ion. So for potassium, it's down here, minus 80 something. For sodium, it's up here, plus 60. Again, in our ideal cell, it was about plus 62. And again, that's for our typical cell. But let's imagine that, in fact, let's just to make it simple, we will close all the potassium channels. So that means we're going to set the permeability of potassium at 0 and for chloride, and we'll just set all three of them. So when we have all three of these, their permeability, that's what this P means, remember, that means that we basically shut all the ion channels altogether. Really, technically the membrane potential is sort of undefined in this situation. So if you actually had a cell with 0 ion channels, in other words, no ions could enter or leave, then all these P's become 0. And then you've got the natural logarithm of 0 divided by 0, which is not something you can do. So there's really not a mathematical way to describe the membrane potential in this situation. But again, there is no real situation in which the permeability to all of these ions would be completely 0. Even with no open channels, there would be some electrical charge that would have the ability to cross the membrane. It's not a perfect conductor. So there would be some membrane potential. And again, these are relative values. So even if let's say the membrane potential, the permeability for potassium is 0.0001, but then the permeability for sodium was 0.0002, then that's double. So in other words, the P for sodium would be 2, the P for potassium would be 1, and so then you could actually calculate the membrane potential. But again, this is purely a mathematical model here. So let's do what we did in our ideal neuron, and let's open some potassium channels. We don't have to open many. In fact, all I have to do is just click, make this equal to 1, and it will immediately drop the membrane potential down to minus, in this case, minus 87, because that's the given these concentrations for potassium that we have set, that's the equilibrium potential for potassium. So right away, the membrane potential dropped down to the equilibrium potential for potassium. And if this graph, or if this simulator showed the current for the ions, you would see that the potassium current right here would be 0 as well. Okay, now let's go back to our ideal neuron, and let's talk about the way that ions move in and out when the action potential occurs. So this is simulating, so far, a neuron at rest. So all we did was open some potassium channels, and that is kind of how neurons at rest are. We'll talk about, or we did talk about potassium channels in the last chapter. So potassium channels are often just left open in neurons, and they keep the membrane potential negative. So that's why the resting potential of most cells is about minus 80. Now it's not minus 80, but why it's usually negative, because of it keeps the membrane potential close to the equilibrium potential for potassium. It's not equal to the equilibrium potential for potassium in a real cell, because there are other ions that do have the ability to go in, including some sodium channels, but that's the reason why the resting potential of a typical cell is usually in the negative 60, 65 range. So now, though, in our artificial cell, so it's at rest. So now let's imagine what happens during an action potential. So again, to start off, we're at rest. So that means our ideal cell has open potassium channels, but all these sodium channels are closed, which means in reality, the conductance for sodium is basically 0, and the conductance for potassium is some number much greater than 0. So again, in that situation, the membrane potential will be equal to the equilibrium potential for potassium. Now let's open some sodium channels. So if we force sodium channels to open, again, you should remember what will happen. So in our artificial setup, our sodium equilibrium potential is a large positive number, so it's plus 62. So that means that there are more sodium ions outside the cell than inside. So that means sodium ions want to come in because of diffusion, but they also want to come in because of their electrical potential, because as long as the inside of the cell is negative, then those positively charged sodium ions will want to come in. So now what we've done is open some sodium channels, and not just a few sodium channels, we've opened a bunch. So we've opened, in fact, more sodium channels than potassium channels. So during this time, the conductance for sodium, the ability for sodium to cross the membrane, is much higher than that for potassium. So we could even just treat that as 0 for potassium for now. Although it's not 0, their potassium ions are still free to go in or out. But as sodium ions enter the cell, that's going to make the inside of the cell more positive, and it's going to continue getting more and more positive until the membrane potential gets to the equilibrium potential for sodium. So again, let's go to our simulator and let's try that out. So again, we've got this set up now where the equilibrium potential is equal to the membrane potential for potassium, and we're going to open some sodium channels. So to simulate that, we're going to raise this value here, the permeability of sodium for our membrane. So if I do that, and it doesn't matter as long as I get a number that's higher than this, but I'll just crank it up. Or actually, I'll go up slowly at first, and you can see that the membrane potential very quickly actually starts to head up and become positive. In fact, right now, it's almost 0 because the permeabilities are the same, and the concentration gradients for sodium and potassium in our little imaginary cell are inverses of each other. But if I go up more, again, the membrane potential becomes gradually larger and larger. And again, you should know what's going to happen if I keep going all the way up. So no matter how high I raise it, it will eventually become equal to the equilibrium potential of sodium. So again, in this particular cell, based on these concentrations, the equilibrium potential for sodium is plus 60 millivolts, 60.6. And again, if I cranked up the sodium permeability by just blowing open all the sodium channels, so that it's much higher than that for potassium, then the membrane potential will come up to the equilibrium potential for sodium. So that means that now the sodium current is 0 because, again, the current is equal to the conductance times the difference between equilibrium potential and membrane potential. In this case, that difference is 0 because it's at equilibrium. But that doesn't mean the sodium ions can't move. It just means that the inward movement of sodium is balanced by the outward movement. And so the net movement is 0. Now, if our potassium channels are still open, there will still be a potassium current. So now, even though the potassium current is very small compared to that for sodium, the difference in membrane potential between the two, so the difference between the equilibrium potential for potassium, which is way down here, and now our membrane potential, which is way up here, is very large. And so there will be a potassium current, but it will be much smaller than the sodium current was because the permeability to potassium is relatively small. All right, so now let's go back to our imaginary neuron and see, okay, we just opened a bunch of sodium channels. Now let's just close them again. So just as suddenly as we opened those channels, we closed them. So now our sodium channels are closed, which means that our potassium conductance is much bigger than our sodium conductance, just like it was in the beginning. That means the sodium current will be equal to 0. And it means the potassium current now will become larger, or will immediately be larger, because again the current is the conductance times the difference between the membrane potential and the equilibrium potential. And now our equilibrium potential or our membrane potential is much higher than the equilibrium potential for potassium. So what will happen is potassium will start to leave. Another word for leaving when we talk about ions is efflux. So when we say that ions are effluxing, or there's an efflux through the membrane, that means the ion is leaving. Influx, of course, is the opposite. That means ions are coming in. And then in this case, what we're saying is that potassium ions are leaving, and eventually the membrane potential will drop and go back to the equilibrium potential for potassium, which again was where we started. So we call that, in this case, the resting potential. One more thing to note about current. Current is defined as the movement of positive charge out of the cell. So when positive ions like potassium leave the cell, again, that's efflux, we call that a positive current. But when sodium enters the cell, so again, the sodium current is going to be equal to the sodium conductance times that difference between the membrane potential and the equilibrium potential for sodium. But the equilibrium potential for sodium is usually positive, and the membrane potential is usually negative, so that delta there will be usually a negative number. Therefore, the sodium current mathematically is negative, and so that's how we define current in this case. So if a positive charge is moving into the cell, even though it's the movement of a positive charge, we still call it negative because it's defined in terms of movement from inside to outside. So now let's go back to our simulator again, and let's see what happens. So we just shut down these sodium channels, and what we see is if we gradually close them, the membrane potential gradually returns back to the equilibrium potential for potassium. And so let's do it quickly just to see what happens if we did what we did before, and just very quickly open and then close those channels. So let's reset our graph here. And so I'll just open and close the sodium channels very fast. So I just open, close. And what you see is, in fact, you get exactly what we saw in the graph, and that's a very sudden rise in membrane potential followed by a very sudden drop in the membrane potential. And it turns out, as we will learn, this is exactly what's going on in the membrane during an action potential. So the action potential is basically a sudden increase in the permeability of sodium followed by a very sudden decrease and then a return to rest. So next time we will talk about the voltage-gated sodium channels that drive most of that process.